Hi, my name is Adriano. In the math department here. However, I'm a statistician and not a mathematician. Of course, that's in my background, but all my career I have studied statistics the whole time. So, in that sense, I want to talk about data science from the statistics perspective. So first, I just want to talk about prediction, which is basically the aim of what we're going to do here today. And I'm going to do that in the statistics point of view because, at least the way I see it, data science, which is probably why you guys are here, is mostly a combination of several tools. Some tools from the statistics field, some tools from the computer science field, and some tools depending on the specific field you work on or the specific field of your data set or what you want to do. So you have to have some knowledge, of course, of that field to be able to, meaningfully interpret the results from your data. But of course, to do those things and to extract this information from the data, you need to have some computer science tools, software, and statistics. And here, let's see if we can look at data science and data analysis with the statistics perspective, looking at the idea of prediction. So, before I even start, I want to ask you a question. If you are a student here today, no matter what your major is, if CSUN had a minor in data science, would you be interested in adding that minor to your degree?
Yes.
So some of them are masters.
Yeah, I know.
Not really.
I'd rather approach those science more in depth, I guess. So
Say it again?
I'd rather approach the topics more in depth than what I'm offer.
Okay.
I mean, like you want a major, he wants to go full on.
So you want to major in data science?
Or in statistics and
Uh-huh.
computer science.
Double major, statistics and computer science.
Well, that's what I wish I had done.
Okay. That would be the ideal if you're interested in the data science world. But the reason why I ask this question is because we are thinking right now in designing a minor in data science. So I don't know if you're going to see that happening, but you may graduate first. But we're designing that, and I just wanted to see your feedback. So that's something that if you were an undergrad or if you are an undergrad, that's something you would be interested in. Is that right?
Yeah, correct.
Yes? Even though it has to add some, units to your total here at CSUN. So the reason why it's tough for us to come up with this data science minor is because you have to have these two things, right? Statistics and computer science, but in order to have the minor, you have to add some of those credits to your overall graduation path. And we're trying to see if we can overlap things with different people, so you don't have to take all the extra credits, but you can double count. So that's what we're trying to do, but it's a tough thing to do. Maybe for computer science students it will be easier because they already have a lot of the tools in their background. Anyway, good to know, but of course you are a biased crowd because you're here because you are interested in data science. It would be easier or better to see a more broad survey of who's interested in data science. Anyway, so let's define at least a few words that I want to talk about data science, not just your idea, but what me, as a statistician, what do I think about data science? So in my perspective, and in many people's perspective, Data science is a collection of methods and algorithms. Methods in statistics and algorithms from computer science. So if you put them together, that's what data science is. Now, in my view, as a statistician, data science, as the name says, is the science to analyze data. But this data is not specifically from any field. So in order for you to be able to analyze data from any field, you need to have these very general tools from the statistics area and the computer science area. Now, what data you're going to use depends on your interests later. But data science is a core, is the science to analyze data, and for that you need computer science and statistics. So that's my point of view as a statistician. Other people may differ a little bit, but this is mostly what people think of when they talk about data science. Now, in fact, data science, this term has only come up a few years ago. Before that, people used to say big data, and they meant data science by big data. But before big data, they were talking about machine learning and AI. So, in my point of view as a statistician, all these terms, they come and go, but they're all talking about the same thing. How can I use these tools to analyze data? Now, when you talk about AI, computer is like learning by itself, but it's learning from data. It's learning from what it observed in the past. So if the computer is talking to you, it's gathering data from your talk, storing it in a data set, and then picking up this data again and again to learn. But basically it's just data analysis. Machine learning or AI is just gathering this data and analyzing it to predict the future. And that's what my focus is here. So if you get this data and you can build some models, you can predict what you're going to say later or what you want, or your likes and dislikes, such as in Facebook or Google ads, right? They always pop up according to your searches, right? You've experienced that, right? You search something on Google and then you're in YouTube watching a video and then there's an ad about those things that you were searching. Yes? Okay. So, here is a little Venn diagram with data science in the middle. If you only have computer science and math, you're doing machine learning. But for me, these two things are almost the same. And then if you're an expert in a specific subject and you know computer science, you can create dangerous software. Other than that, all the combination. Can you read everything? This is computer science. This is math and stats. In the middle, you have machine learning and data science. This is subject matter expertise. And if you're very expert in a field and you're very good at computer science, you can build dangerous software.
What is that? What's dangerous software?
If you're really expert in chemistry and stuff like that, and you know how to combine things, you can hack someone's lab computer which automatically deals with chemicals and then explode it or something like that. Many other examples, but you can think of them too.
What's on the green side?
The green side, traditional research. Yeah, when you're doing research in biology and you call a statistician, hey, I need to analyze my data. That's traditional research. Does that make sense? Okay, so this is one of the most famous statisticians. His name is John Tukey, and he said the best thing about being a statistician is that you can get to play in everyone's backyard. And here you can replace statistician for data scientist. So this is what I do all the time, because as a statistician I have all the tools to analyze data, but I don't have the data. I have to talk to a biologist, to an engineer, to a geologist, and they have those observations. They collect the survey and all of that. So I help them, so I go to their house, their backyard, and I play there. So that's the idea here. And yeah, this is basically what data scientists do. And of course, data scientists have more computer skills than I do as a statistician. Now, here is my view of what this is really doing. So here you have statistics, it's a crack in the wall, you put a frame on it, you call machine learning, and then you go in front of the crowd and say, this is artificial intelligence. But what it really is just using statistical methods with, some coding experience, because sometimes you need loops and functions and stuff like that. But really to analyze the data, to predict the future, which is my goal here, is doing modeling. Statistical models will predict the future. Computer science by itself will not. Just code. We need the model to predict the future. And AI is basically trying to predict stuff, right? To learn from what was in the past. Now, where do we need to predict outcomes and why? Here in Data Jam, you have the challenge to do something with your data. And as I see it, there are a few things that you can do, but the most impressive thing that you can do with data is to build a model that can predict something. Of course, looking at exploratory data analysis is awesome because you can get ideas of what to do or what happened or how things are. But if you can build a model to predict something, that can give you more of a decision-making process to make decisions that will impact the future. By predicting that the water levels will grow, right? So if you can't predict that, then you don't know that it's growing, so you can't take any action. But if you model the environment, the climate, or whatever it is, to predict that the water levels are growing, then you can create some type of construction, raise barriers, I don't know, whatever it is. We have to predict that. Now, where else do we do this? Of course, here in Data Jam, you have a few data sets that you can work on. But in other places, you can think of any type of data sets to predict stuff. For example, in the internet, or the advertising business, which is always in the internet, as we were saying, Google tries to predict your likes and dislikes and what you will buy in the near future. And the reason to do that is because Google gets money if you click on the ad and you're forwarded to the website of the company trying to sell you whatever it is, shoes, beer, whatever. So by predicting what you need, Google can make more money. Now, in hospitals and pharmaceutical industry, what do we really want to predict? What are examples of things that we want to predict with data sets from hospitals, meaning medical data sets or pharmaceutical data sets?
Disease outcomes?
We want to predict the likelihood someone will have a disease based on other people that are similar to that person. Similar in the sense that they have the same type of measurements, let's say waist circumference, height, blood, cholesterol, and other measurements. So using those measurements, you want to predict if that person will have this disease or that disease. And you see that all the time out there, right? People say, well, if you drink a glass of wine a day, it reduces your chances of getting whatever disease. So there's always stuff to predict. Now, autonomous vehicles is something that I work on as a statistician. And I'll show you a couple of things that I've done. And what do you want to predict in autonomous vehicles? It's obvious, right? Safety, and as the vehicle starts driving, what do you want to predict? Other car movements, right? I want to predict where the other cars will be so that I can avoid that route, so I can go around them and not crash, right? So predicting the future movement of other vehicles is what people do in autonomous vehicles research. And this is, of course, a hot topic everywhere. And I, as a statistician, do stuff on this, and I'll show you a couple things. So you do want to, so you see, all that I'm talking about here is about predicting the future, right? Predicting future observations. Now, last week here at Data Jam, I was talking about, so my suggestion to all the people who stopped at our table was, be creative. And I repeat that, and I repeat many times. Because many times you have a data set, and you might have a question. How does this variable relate to that variable? But other times you don't have a specific research question, and you need to be creative in trying to see things that are not already asked. So can I relate data sets? Can I put variables together? Can I combine things so that I can predict the other variable that I want better? Can I combine images to be able to predict a disease? Because sometimes you have the 3D scans, what are they called? MRI? So you have to be creative in data science. And prediction is one of the things that you can be most creative about. Because let's say in an autonomous vehicle, you want to predict the position of the other car, but you also want to predict where you could be given that the other vehicle is taking that route. So I could go their way, or I could go this way, which one is better? So you can be creative in many ways in all these areas here. Stock market, so you can make more money. Advertising, also money. Biology, microarray, this is reading genes to predict the disease. So there's a ton of things to do. But you guys in Data Jam are just specifically going to talk about resilience. So let me show you a couple things about autonomous vehicles here. Let's see if we can go. There you go. How do I do this? Is it opening or what?
Is it control click?
It's just clicking on the whole thing.
It's a PDF.
Ah, it's a PDF. Oh, I might have the other one. So this is the DARPA Grand Challenge. It actually started, I think, in 2004, many years ago, in the desert. You just had to predict, have your vehicle drive through the desert, avoiding rocks and stuff. Nowadays, the prediction is, of course, on the streets. And I think this first one, this is the Department of Defense. I think this one was 2007. So now you know this is very common. You see the cars out there with the radars on top, right? So this is very common nowadays. And this is a little video of the cars, but of course you already know this, so I don't want to waste too much time here. But you see, this is the original DARPA Grand Challenge in the desert. All they had to do is just follow some type of routes and arrive as fast as possible. Then this is the video in the city. You've seen the Google cars around. So these radars here are called LIDAR or LIDAR. I'm not sure how to pronounce it. LIDAR. And they just send basically laser beams, and then they capture the distance and they can map the environment. But now the question here is, I don't know if you have seen this before, if you're engineers or anything, but what is the statistics point of view here is that these radars, they're not exact. They have some measurement error. So when you create your environment reading by the laser beams, there is some noise associated with this. And noise means error, which is basically what statistics deals with all the time. So this is a little bit of what I do. Let me see if I have in the slides a link to my page where, yeah, hold on, let's see. Yeah, this is on my page, but let me show you real quick what I mean by modeling this in the statistics perspective. So here you have, this is my research, okay, so this is what I do. You have, this is your car. So I'm just putting circles because it's easier to see. So this is your car, and you want to go from this position to this position, but it could be anywhere. So you just want to go straight. There is some stuff on the way here, and there are all these other cars or trucks or whatever they are, and they're all moving. And you see some of them are moving in a curved linear way, others are moving in a straight line. So all of them, they have some direction, speed, and velocity. So by using, this is simulated data, it's not really real data, but simulated data, you can see the obstacles, you can see them with some noise, then you can predict the future. So the idea is something like this. So you can see here that the black points are where they're supposed to be, but I really observe the red dots, so there's some noise. And then I have to predict where these guys will be in the future so I can avoid them. So this is the idea. And you can do this with statistical modeling. So this is the idea. Now, let me show this cool application that I have. So this is my web page. You can go here to here. No. Here. No. Where is it? Maybe go to publications and then go all the way down to robots path planning. So here is a simulated example. This is my car. This is the trajectory that I simulated, and you can play the present time or the future time. So here, let's see, yeah. So you see, these guys are moving, so these are the obstacles in black, but around them you can see ellipses, right? So they look like circles, but they're really ellipses. And they're just giving me some confidence so I don't crash. So this is what happened. You can see that the trajectory is being updated every time, right? I'm updating the trajectory. As I move, the trajectory changes because I'm reading more data, just like machine learning or AI. You read more data and you see how bad it was before, but now it's getting smaller and smaller and smaller. It's almost like a straight shot. So I'm updating, learning with the data to make better predictions and then be able to go further. Now, let me play the future time. Pause. Let me reload this. So I'm going to play future time. And this is the ellipses. You will see that they're growing. They're growing with the obstacle. You see how the ellipses are getting bigger and bigger? Because this is what happens with prediction in the future. If you want to predict something tomorrow, let's say the weather, it's easier than to predict the weather 30 days from now, right? So it's much easier to predict something right in the future than it is far in the future. So here these ellipses are growing because I don't really know where these obstacles will be. I have all this prediction area where they could be. So I have to avoid the whole ellipse. But of course, there is a time that is so hard that I just can't avoid anything because the ellipses are huge. But basically, when my car is here, if I update, as you saw in the previous video, the ellipses get smaller and smaller because I have more and more data, so I can update. In this case here, I'm not updating, I'm just using the initial information. So predicting the future here is what we really want to do. Are there any questions here, concerns, comments? Yes.
What kind of path planning algorithm that you're using?
So I have a statistical model to predict where the obstacles will be, and this model is based on maximizing the probability.
Oh, so it's machine learning. It's not like computer science.
Well, it's
algorithm.
both. It's both together because, so what I have is I have my data, and it looks like this, as I actually have in the slide here. This is what my data looks like. This is what my data looks like. The first obstacle, I have the position, and then the next position after however many seconds or milliseconds I have. And then position, position, position. So you see that this guy here has the X position fixed and the Y position is changing, so it's just moving up, right? So I can put a model in here because the model is linear. I can just use a line model. And then of course there's the error that you saw in the previous graph. So I can model this with the epsilon. If you have seen, statistics regression before, and we'll talk a little bit about that. The epsilon is the error, so those points that are red like this, those are the errors. So you model this to estimate where the guy will be. Now, to answer your question, is this machine learning? What is it? In order to find my trajectory, the red that you saw here, I need to optimize this model. So to optimize this model, I have to get the data, predict where they will be, and find the minimum path that takes me there as fast as possible. So this is, you can say this is machine learning based on the data that I have. But I'm not doing a specific, let's say, logistic regression or KNN, if you've heard about those. I'm not doing any of those. I'm doing my own model.
Okay. Yeah, because I try doing object avoidance and navigation in autonomous car, and I remember that I was using A star and stuff like that now, machine learning. So.
Right. So A star is an algorithm to look for the maximum or minimum of something, right? So yes, I'm not using that algorithm. I think in this case I'm using genetic algorithms to find the minimum of this function. Yeah. Because this function here is just it's a regular function that I make it smooth, and then to find where that function will be, I use genetic algorithms. Yes.
Okay.
Did you have a question?
Yeah, so in this illustration, I know it's not like perfect or anything, but the two stationary items, why would their ellipses be growing at all if they're not moving? Like,
Right.
so you would predict that if it's stationary and it's been stationary, it stays stationary, right?
Right. Good question. The problem with the stationary objects is not that they're moving or not. So imagine if you're stationary, but you have your radar, right? Your LiDAR radar. And every time you observe that guy, you observe with some error.
Right.
So basically, you don't observe the center. You observe like some error like this all the time. So as you get more and more data, more and more observations like this, then your ellipse shrinks. But what you're seeing here is all this path is the future.
Right.
So when I'm here, exactly at this point, I have, let's say, 5 observations. Because when I turned on my car, the thing turned on, and I have 5 observations. That's it. So from here, with 5 observations, I have to predict everywhere the entire time that I will need to go all the way here. So the ellipse around this guy is just giving you some room in case that guy was moving but I wasn't sure. Because, I have 5 observations like random, maybe it was moving very slowly in that direction, but I can't tell
Right.
because I only have like a few points like this.
Right. Okay.
Does that make sense? And if you, look, if you stop, future, and if you play the present time, so here's where I am right here, and you will see that the ellipses will not grow anymore because I'm going to play present time, which means that every step I take, I get the observations and I update my machine learning method. So here's the present time. So you see that the ellipses are not really growing. They're actually shrinking because every step I get more data and I am more precise, so I can shrink those confidence regions.
Okay.
Pretty cool, right?
Yeah.
I love this. This is a clear example of predicting the future, which is really what I want to talk to you about. Okay, so this is basically the data I have. So with this data, I have to create my model and use some machine learning algorithm to predict what's going to happen next, minimize my function. So this is what I do. This is one of my research projects. Okay. So microarray data, I also do some research on microarray data. I want to predict, for example, the likelihood of certain disease, let's say cancer or no cancer, based on your gene expressions. Now, what is the biggest problem with gene expressions? You might find some problems just like this that I'm talking about with your data sets in DataJam. I'm not sure if you will, but you may. What is microarray data? You basically scan all your genes, and you want to predict if the person has disease or no disease, cancer or no cancer. But the biggest problem is, how many genes do we have?
About 20,000.
A lot. We have a lot of genes. Each gene is basically a variable, a column. And if you have too many of them, thousands or sometimes even millions of them, how can you use all of that to predict disease or no disease? Right? So there's a question there that you need to answer. You need to see which genes really contribute to the likelihood of cancer or no cancer. Because many of our genes don't really matter, right? Some of genes are just telling us our height, or others the size of our toes, or something like that. But some genes specifically have high correlation with some type of disease. So here what we're trying to do is select. And this is called variable selection, right? But why are you talking about variable selection if you're talking about prediction? Why do I have to do variable selection if I do prediction? If I'm interested in prediction? Can't I just use all the variables? I want to know your perspective. Why would you like to do variable selection if you want to predict something? Imagine your data set is long, have lots of genes, and you want to predict cancer or no cancer. Can I run the model with all genes? Or should I reduce the number of genes and only select a few of them to help me predict? Why? Why is this something that we would like to do?
To get a more precise, like you reduce the number of betas that you have to look at. Find the ones that are impacting it the most.
Yes. More ideas? Yes. That is correct. Yes. More?
Computational time would be another.
Yes. See how it's good to have statisticians and computer scientists? Because we can use ideas from both fields. Yes, we need less computer time because if you have millions of genes, it's just going to take forever. Your computer may crash. You may not be able to get the output from the software. What else? Because of prediction. And I want to emphasize here, prediction, in this idea that we're talking, is different from estimation. So if we use all the genes, that will definitely give me the best R squared, if you know R squared, is the coefficient of determination, which tells you how good your model is fitting. It's like a goodness of fit type of thing. So as more variables you put, your r squared will always increase. So you want to have a better r squared because it seems like you're explaining more and more about the model. But that's not true for prediction. So explaining the model relationship between your predictor variables and your response variable means that the residuals are small, but the prediction error might be large. Because if you get a new person in the hospital, you're going to read his genes and see if he has cancer or no cancer, that prediction might be falling out of the model that you got. Because your model is just trying to get closer and closer to all the points. But a new person might not be close to these points. It might be a little bit off. And then your error is just going to be too large because the model went over here to this point, but the new person is here. So they're far apart. So your model has to go, let's say, a line, and not really go point to point, right? It doesn't make sense. If you see the cloud of points, which is a linear regression, you don't want to go point to point like this, right? You just want to see the line, which is basically explaining the trend, but not every single step. So in prediction, you're going to lose a lot if you use more r squared. So reducing the number of variables, computational time, it explains better your model because you can interpret it better. And it's going to help you with prediction, which is what I want you to take from this little workshop. Prediction, prediction, prediction. Yeah.
I was just thinking, like, a million predictors or thousands, wouldn't like multilinearity stuff be a bigger issue? Like more, like even stuff that does predict disease wouldn't show up predicting it because it overlaps with other genes.
Yes.
And so it looks like nothing predicts anything because you have so many predictors, right?
Yes, excellent question. There is nowadays a lot of research in the statistics field about what to do when there's too many variables. There are a few things that you can do, and I have actually a couple papers out in this area, and one of the ideas is super simple, but it was theoretically proven only in 2008 that if you have all these genes and you have your response variable, whichever it is, you can look at the pairwise correlations. Correlation from the first predictor to the response, second prediction to the response, and correlation coefficient. This is Pearson, for example. So this correlation coefficient is 0, there's no correlation. This correlation coefficient is very high, 0.99. This correlation coefficient is 0.5, it's okay. This correlation coefficient, so you get the variables, the predictors, and you pick those which have very high correlation with y. How many of those you pick, then you have to manage the size you want. But after you do that, so this first is called screening. So you screen out things that you don't want. You pick stuff that is highly in terms correlated with the response, and from those, then you can run a model or even run variable selection again on these. But the first step of millions of genes, thousands of genes, you can do this called screening, which is sub-selecting only the high correlations with the response. And the theory was proven very recently in 2008, and then now a few papers came out. I have a couple of papers in this area too, to prove that this method makes sense as your number of patients, for example, increase. Of course, if you have 10 patients, it's going to be hard. But as the number of patients increase, this method works better and better, which means it's consistent. So you do whatever you can with the number of patients you have. That's the idea. Yeah? Okay. So here's some of the stuff that we were talking about. Here, Facebook ads, I mentioned it. You want to predict the buyer's choice so that Google will get more money because you clicked on that ad. So predicting the choice is very important. This is Facebook and Google, they do this all the time. And they do it based on your information. So you have the predictors, again, is your profile, basically, with Google, and all the surfing data that you have, all the clicks in the past that you have. So you can think about it as machine learning or AI again, because all this data is in their data sets in Google, and they use it to predict what you want to buy tomorrow. So this is an example of how a simple data set in this case would look like. So you have here dates, times, whatever you did, you looked at a picture, you clicked on it to open it up, or you watched the video, and this is like say as a Facebook type of data set. Or you liked someone's page, and you also put a comment, and maybe sometimes you have keywords or the information about the object that you were looking at. So you can think about all of these things and how to use them to predict people's choices. So it's, again, in this case here, I go back to the message that I give you, creativity. Because you can use it, because this data set is very simple, right? This data set, Facebook, I'm sure there are tons of things that you can look at. So you need to be creative to see what connects with what and how to connect things, and get external data sets to use, which you should in Data Jam. So all these things are really interesting. Any comments here? Please comment. This is a nice conversation that I want to have. I don't want to be just talking. Any comments, views, ideas, concerns? You want a job at Facebook? I can hook you up. Just kidding, I can't. It would be nice, huh? No, but I don't have that connection yet. Maybe I'll get a job there. Okay, so here are things that can be in your data set. This advertising, matching the data. So here, classification. So classification is what most people think of when they say machine learning or data mining, is to classify. Based on the data, you want to classify the type of person or the type of object. So, of course, they do this all the time also in many other internet companies. There's also dating websites that use this prediction, right? And they actually use their prediction ability as their advertisement. Because as you match people, let's say they get married or they start living together, this is a correct prediction that they would match. So they use this as their advertising. Oh, our match is 80%, 90% of people have long-term relationships after we match them up. And matching them just means that you're predicting that they have the same lifestyles or something like that. So again, there's a lot of creativity that you can use if you work in these companies. There's a couple of models that they use. This is a classical example in statistics. Have you guys seen this body fat example? No. So body fat is, you want to predict the percentage body fat in someone's body based on some measurements. Let's say the wrist circumference, the neck circumference, maybe the height, and even the weight. Because you know, they're not exactly linked one-to-one, your weight in percent of fat that you have in your body. Even thin people can have somewhat large percentage of fat in their body. So this is a very classical example in statistics, and the data set is free for you to look at in here, Carnegie Mellon University. So you can look over there. There are 262 men in this data set, and this is a classical example of multiple regression. Now, are you going to use linear regression or non-linear regression, non-parametric regression? That's your choice. And here are just a couple things from this data set. So you have age, weight, height, neck circumference, lots of circumferences here. And then they actually measured the body fat percentage based on this series equation with underwater weighing. So now you have the data sets, and if there's a new person, you just measure their measurements, and then you can predict, well, what is their body fat percentage. This is actually another research that I did in Chicago, because I was in Chicago before coming here. Here is trying to predict crime. Of course, when we talk about Chicago, everybody thinks, oh, crime, right? So this is a study that I did with my undergraduate student. This is data from 2003 to 2017. And you can see this is basically the heat map, and this is just a regular scatter plot of the crimes. So each dot here is a crime. And these are crimes related to sex offenses in Chicago. And this is also the intensity or heat map for crime offenses, sex offenses. And as you can see, this is 2003, 2007, 8 to 12, 13 to 17. You can definitely see how the heat map is going down, right? So everybody's saying crime in Chicago is increasing, it's crazy, it's increasing crime, but that's not what we saw with the data. So maybe it's just a perception of people. But our model predicts that, of course, there's some variability, you know. In the summer there's a little more, in the winter people are inside, there's not as much crime. But the overall trend is that it's decreasing. And it has been decreasing since the early 2000s. Now, I think this year there was a little spike on the gun crimes in Chicago. But they're all different types of crimes. There are sex offenses, there are batteries, there are gun-related, and there are other types of crimes. But most of the crimes we saw, all were trending down. So we predict that it will continue going down slowly, of course, but it will. Concerns? Questions? Okay. Here's the data for crime in Chicago, and let's talk about talking about things, and let's talk about other things. Okay, so if you're familiar with regression, that's good. So I hope I don't bore you, because this is a little bit about regression. Maybe I'll give you a little bit of perspective on the statistics point of view of regression, and maybe that will be some new information for you. So this is in R. So you can actually go right now, if you have R open, and you look at this data set called Faithful. Have you guys seen this data set? So just go into R and type Faithful. It should give you the data set.
I think ours open, go ahead and show them.
Oh yeah. So here it is. I just typed Faithful, and the data sets came up. So there are two variables here. One is eruptions and the other one is weighting. So Faithful is the name of the biggest geyser in Yellowstone. And it erupts every certain hours or minutes. And here is the waiting time, I think in minutes. And this is the eruption time, how many minutes the eruption lasts. So we're trying to see if we can predict the eruption time based on the waiting time. And here is basically what you see. But funny enough, there's kind of a gap here in the middle, right? It's not nicely spread. But still, you can see a definite linear trend. Now, this is what I was talking about, the prediction error before. If you try to fit a model with a very large R squared, you're going to basically connect all these points like this. And then when you try to predict someone here, it's going to be bad, because from here you're going to go to this point, so your prediction error doesn't make sense. So having the straight line there will help you predict the trend, which is basically what we want to do in this case. So can we predict the eruption time based on the waiting time? Yes, because we have a linear trend, but we need the model. In this case here is a simple regression model. And I'm almost sure you know regression. And if you don't know, regression is just a line that shows you the trend of the data. Now, a regression line, of course, if you remember from high school, is just intercept a plus bx. And now this is the error, which is what us statisticians do all the time. Without the error, it's just mathematics. With the error, it's statistics. Now, the whole point of this is to minimize the error. We want to minimize the error, and this is what I did with the autonomous vehicle, right? So I want to arrive there as fast as possible, minimizing the error, which in my case is crashing the obstacles. In this case here, minimizing the error means I want to minimize the distance between my line and all the points, as long as I have a line which tells us the direction. So response variable and predictor variable, eruption time and waiting time, and then the parameters beta 0 and beta 1, and the error term. So if you know this, it's just boring, but it's okay. So the first thing you need to remember when doing regression is that there are some assumptions. So the first assumption in this case is that it's a linear model. Because if you don't assume that the model is linear, then it can have any form, and you have to apply other techniques to be able to solve the problem. But regression, in minimizing that error over there, squared in fact, is based on the linearity assumptions. But there are other assumptions that we need to check. So when you do use your data sets in DataJam, make sure you remember what the assumptions are. If you're doing regression, or if you're doing classification, or whatever you're doing, make sure you remember what the assumptions are. And why I say that? Because the judges will know if you know what you're talking about, or if you're just, I ran the regression, I got this result. By saying, oh, the assumptions were met, the errors were normally distributed, there was no trend in the error, and all of those other assumptions that you need in regression. If you don't have those, then it doesn't matter that your model is predicting well, because your model will be wrong in the future if you have new data points. So you have to remember the assumptions. First assumption, linearity, and there are other assumptions that I don't want to go in details with you because this is not a regression class. I just want to give you some perspective on the statistics point of view. So here is the function to run regression in R, LM. If you have done this before, you know what it is. There's also a GLM, which is more generalized. You can use that one too. But you can go ahead and run this to see what happens. So I'm going to run it here too. How do I select this? How do I select it? Here.
So those are your unstandardized betas, right?
Say again?
Those are your unstandardized betas, right?
Yes.
Yeah.
Where? Here. No. Yes. No. How do I select this?
Should be just the arrow one.
Because this hand is not going to select. Ah.
Yeah.
Yeah. So here are the betas. Minus 1.87, 0.07. So this is the slope, or how fast my line is growing, and the intercept minus 1.87 is where the line will hit the graph. Let's see if I have it. I don't have it, but we can do just a plot. So I think you just do plot. Oh, this is getting the residual. So I think I have the code here. Where's the code? Here's the code to plot the line and everything. So first you plot the scatter plot. So this is just going to plot all the points. I need to do the tilde. Didn't get it? Okay, so this guy here plots just all the scatter plot here, and then to plot the line, you do AB line. After you create fit, you have to create the variable fit. So you put the line there. Now, the biggest question here is, what happens if the waiting time is, let's say 60, 50, 40, 30? What happens if the waiting time is 30? So here's my prediction, right? So the line is my prediction. So if my waiting time is 70, my prediction is that the eruption time will be about 3.4 seconds or minutes. But what happens if my waiting time is 30, which is here? Somewhere here, right? So my prediction is that the eruption time will be negative. Does that make sense? Can we have an eruption time that is negative? It's just sucking instead of eruption, sucking it back.
You mean like inverse? Or?
Yeah. So this is a concerning question, right? So what happens if my waiting time is because all my data? See, all my data is between, let's say, 40 and 100 minutes, right? But what if my waiting time is 30, which is all the way here, and I have no data there? What do I do? Can I predict the eruption time? Well, I could, it would be negative. But does that even make sense? It doesn't make sense. So here is another tip on the statistics side of prediction. If the prediction is outside the range of your data, you shouldn't do it. Never do it if it's outside of the range of the data. Here's the range of your data from 40 to 100. If it's outside, don't do it because it doesn't make sense. Even if it made sense, let's say if you want to predict 35 and the prediction time would be 0.5 or half a minute, it does not make sense to predict outside the data. So if you're doing data jam stuff and you're trying to predict and it's outside of the range of the data and the judges see it, you're not going to get the points or the prize. Same thing with if you're trying to predict a grade based on sleep hours. So if the more you sleep, you expect to get better grades because your brain is, learning more because you're sleeping more, so retaining more. But there is a limit, right? You can't sleep more than 24 hours a day. So there's a limit there. It doesn't make sense to predict your grade sleeping more than 4 hours a day. So outside of the range of the data, never do it because it just doesn't make sense and it's statistically wrong. Okay. So here is testing the relationship, and why do we want to test the relationship? It goes back to the question of having tons of predictors. If some of your predictors are not significant, you shouldn't keep them. And this is Andy's question. What do I do if I have many of them? You test each one of them individually. And you can test them by using a hypothesis test like this, and you might know how to do this. Or you can just test them by looking at the correlation between each predictor and the response. But here is a different way of testing their, if you can rely on that predictor, is testing if that beta is equal to 0. Because if it is equal to 0, then you don't need it. because it's just 0. So to test that, you're going to look at the p-value and the test statistics, and here is how you do it. Just look at the summary of your fit. So if you have R, you can just do summary of your fit. Fit. This is going to give you the p-value. If the p-value is very small, you reject the hypothesis and you keep the predictor, otherwise you just throw it away. Okay, what else? Here's the output from R. You already all know all of this, so I'm going to keep going. So here's prediction. If you are at 62 miles per hour, and this is the cars data set, where's the cars data set? So you just go to R and type cars. So here's the data set, and you have speed and distance in the cars data set, and you're trying to predict the distance that you need to stop the car based on the speeds that you're driving. That's the idea here. So distance is your response and speed is your predictor. And again, you can fit the model, tests, everything else that you already know, I think, most of you. But the idea here is not to teach you regression, because that's a semester course. Just want to give you some perspective on what you can do here. So I want to take a few minutes here. So here's the coefficient of determination. So we already talked about this guy, and this is really key. And I don't know if you've seen regression before, if you emphasized enough on R squared. Because R squared, although is a goodness of fit measure, and you want it to be high, you need to be careful with overfitting. And overfitting is what I said. You just fit very near all the points, but your prediction is usually bad. And if you do machine learning, you know how to fix that. How do you fix that with machine learning? If you're trying to do classification in machine learning, K&N algorithm, logistic regression, and stuff like that, how do you try to fix overfitting to improve your prediction power? What can you do?
Clean and screen your data.
Say again?
Clean and screen your data.
Clean your screen of data is the first step, that's right, and if you don't do that, you're going to mess up everything. But after the model starts, can you do something?
Yeah, reduce the training data.
Say it again?
Reducing the training data.
Yes. You said a keyword, training data, right? So you have to see the balance between the training and the test set. So this is, I don't know if you've heard about training and test sets. Have you all? No? No? Okay, so what is training and test set? So you get, and you can do this in regression too. Okay, classification is more classical, but you can do also in regression. You have your data set, and if you fit your model using all the data, you're gonna get some R squared, which is the goodness of fit. You're gonna see the line, and all great, all beautiful. Now, how do you know if this model that you just built with this data set is good to predict new people that come to the hospital or new cars that were not in your data sets? How do you know?
Well,
One-
we have a,
Go ahead.
oh, you have a test data
Right.
that you haven't, feed the model with.
Yes,
So you test that model on that test data.
exactly.
To see if it,
Exactly. Perfect. So you break your data set into two pieces. One piece is going to be called test set, and you're just going to leave it behind in your pocket. And the training part, so training and test. So the training, you're going to build your regression model. And the test set, you're going to use as a pseudo new data set to see if the predictions are good. Does that make sense? Yes? You that have never seen it, does that make sense?
Yeah.
So build your model, your regression model, get the line from this data set. And then the other one that you left in your pocket is called test data. You check the predictions. And how do you check the predictions? Well, you have the y variable here, right? Because your data set is full. This test set is full. You have the response variables and you have the predictors. So you feed the predictors in the model and you get the prediction from the model, and then you check with the y variables to see if they predicted well. So you can check the prediction of your model. So this is key in many models in statistics. Classical for machine learning and data mining, but you can also do it in regression. So very important. Any comments, questions, concerns? Sad faces, happy faces, anything? I see happy faces. Good. Okay, so we already talked about the R-squared, so that's, if you want to check your R-squared, look at training and test sets. It's very useful. And then there's another keyword called cross-validation. It's kind of a similar idea, but in a different way. But you can look that up too, cross-validation. So, how many of you have seen time series before? Method, statistical method, time series. Called? Yes. Okay, that's good enough. Which model did you see?
What are they used to analyze the EEG? The time series to analyze the MRI EEG results.
Did you see?
Saw it, didn't understand. Walked away, I don't remember.
That's fine. Have you, any of you heard of the model called autoregressive or moving average, or the combination of those called ARMA? So this is what one of the models for time series that you can use. I'm sure that I'm not gonna, this is a 6-month course or more here at CSUN, so I'm not gonna go into details, but I want you to know that they exist. That's what I want to tell you. And what does a time series model do? Predicts the future based on timely observations. So when you did regression, you have your eruptions time, eruption period, and the waiting period, right? But you're assuming that all the observations are basically independent. Whenever you're trying to get the distance to stop based on the speed of the car, you're assuming that you have different cars, right? That's the idea. What is a time series? A time series, and you might find that in your DataJam data sets. I'm almost sure there are things there in your DataJam data sets that are observations through time. What are examples of those? If I get the height of my kid, does the same person being observed through time, right? It's the height of that person and then the height of that same person, the height of the same person through time. Or if you're looking at the water levels, so the water levels through time, right? So actually the water levels, they go up and down, right? But it's the same measurement you're doing, water level, at a specific beach. Or you're doing the grades of a student through time, through high school. Or you're doing anything that is through time, you can model with time series models. Now, I'm not going to go into details, but I'm going to tell you what they are, and if you need, you can do more research, or you can ask me, or you can ask other people about time series models. What are these models? So here, there's of course the most classical example in time series is the stock market, right? It goes up and down, and people want to predict the future of the stocks because they want to make money. They want to know if the stocks are going up or down. So predicting that is really important to make a lot of money. Of course, there's air quality, temperature, and all of those things. So here is the model that I'm telling you, and you can do your research, so I don't want to go into details, but here is the model. It's called ARMA, but in this case you have an I in the middle, which means you're taking a difference, but that's something we can explore if you take a data science course that has time series, or if you take a time series course. But I want to point out that it exists, and you can do your research. You can go into R, and you can look at the help file, and you can look on Google, and see how people do it in R. So here's the function, and I want to show you what that function is. So if you just type arima in R, it's going to pop up the function. Okay? So if you know how to look at help files in R, you do question mark, and then you type the name of the function, question mark arima, and then you can open it, and it's going to tell you what it's doing. So here you have arima modeling of time series, and here this X is going to be your time series. So of course I'm not going to tell you all the details, but what you do is you just feed the time series to the arima model, and it's going to spit out some results, and then of course we have to interpret those results. But this time series here, X, is just a data set that is going through time. Whatever it is, the number of air passengers flying in an airline, or the height of your kid, or something like that. So let's take a look and quickly on this example that I mentioned here called air passengers. So if you have R, you can just type air passengers. So here you can see the time series, right? So it starts in 1949, and it goes, so let's see, the time goes this way. So this ARIMA model, it can adjust different ways of your data set. So in this case, it's just month by month, year by year, and you can use this. Now, let's see if we can just run this real quick. So here is fitting the ARIMA model, look. Just fitting the ARIMA model, it's giving the air passengers here as a data set. It's just taking the log. I don't know why it's taking the log, but it doesn't matter. And here are the things that you need to input. You need to select your ARIMA model. How many times you need to look in the past. So this is basically, so this is 0, 1, 1, 0, 1, 1. It means that you have to look in the past one step to be able to predict the future. Right? So if you want to look many steps in the past, then you increase those numbers to 2 or 3 or 4 months. But basically here, you're just looking at 1 month in the past. So I'm just going to run this for you to see how it runs. Here it is. So it did run the model. It estimated these coefficients here. And these coefficients, they're similar to the regression coefficients. The regression coefficient just tells you how fast the relationship is growing, right? So these coefficients are helping you predict the future based on the past. So basically, it's the coefficients that you need to the past to be able to predict the future. Of course, we don't have time for all the details on this, but I wanted you to know that it exists because I'm sure that there is stuff in your data sets that is timely observed, right? Have you guys seen the data sets? Is there anything that you remember that is observed through time in the data sets?
I don't think they have the data yet.
Yeah, it's all up.
Oh, it's all up?
Yeah.
It's all, oh, I didn't know it was posted.
Yeah. Open data sources. So,
Oh, okay.
No? Have you guys looked at the data sets?
Okay, it's time to look. I didn't know and you didn't know, but now we know.
Yeah, so
So how does it, can we explain that, Andrew? So how does it work about looking at the data sets?
So on the Canvas site, there's like a list of a bunch of data sets that are all city data sets that are basically like the base data sets. I think the rule, I'm not 100% sure on this, like we have to ask Sherry, but the rule for data set this year is that as long as you use one of those data sets, then it sort of is good. Like that, you know, you can combine it with other data sets that you want. Actually, there's even one of the award categories is to use external data to combine with those data sets. But I think you have to use one of those and on the list. that are, it's on, I can show you when you.
Yeah, because I don't think it's, like, I'm assigning my class to work on this, and I didn't realize that that data was,
But, so the thing is, the theme,
Yeah.
because the theme of the issue is like resilient LA, so it's all like LA city data. Most of that stuff, it wouldn't be that easy to, it wouldn't be that hard to combine. Because if you find city data that has like any kind of geocode, you know, like even zip codes or whatever, you can combine the data from other sources. And now you're using that data along with new data to, you know, however you want. I mean, it's just there has to be some connection to the LA city data some way or another. I can show you where.
all right, well, that's great.
Here, the-
Interrupted.
The data, I can show you.
So do you guys have any questions specifically about statistics and the point of view of statistics at Data Jam, or anything you would like to ask me, my favorite caller, or anything?
I'll definitely be sending you an email about it.
Yeah, sure.
Yeah. That's fun.
Yeah, we should, hopefully we'll have this data science minor soon, and maybe one day a major or even a master's program, who knows. But you're always welcome to contact us if you have questions about statistics and, you know, ideas. We can't do the work for you at the Data Jam, you have to do it, but we can, you know, be there to support you.
On the, this is the Canvas, the Data Jam, the linking Canvas page. On the very top of it was to start here. I don't know. A little one halfway down is a link that says data sets. And then click on that, it takes you to here. It's a bunch of them. This is all, it's all data that LAC.org is where most of it comes from, but there's also from LAC GeoHub and there's LA County data as well. So there's a bunch of different data sets. And even within each of these links is multiple data sets within, you know, each one's linked. It's grouped by like business and boundaries and the health and infrastructure, planning, recreational parks. So there's different topics that relate to it. So you just got to find the topic that you were interested in and then find ways to connect it to the data you want to use. So instead of, so last year the data was completely like cleaned and curated and put together by the Data Jam committee and then sort of released. And then we realized that, I mean, I think we realized ahead of time, but I think because the first time we were trying to make it like really easy and really compartmentalized so that it was, the judging, everything was sort of simple to sort of figure out. But then we realized that most of the work that data scientists do is the stuff that we already did for you, which is the cleaning and the you know, putting stuff together. So we're like, so we just back up a little bit. We'll give you data that we know is at least not a complete mess. The stuff's not perfect, but at least it's, you know, it's fairly, I wouldn't call it clean, but it's organized in a way that makes sense anyway. And then, you know, so here's a list of those, you know, usable data, and then sort of go from there. So you have to do some cleaning and curating yourself and put together data sets. All right. Any other questions for Adriano?
Is the presentations going to be available on campus or anywhere?
Like the slides here, if you send them to me, I can post them on there. Yeah, it's fine.
Yeah.
So a lot of times we're never sure if the presenters are willing to do that or not. So usually we figure we'll ask and then we can make it available. What we'll probably do is on the list of topic workshops that were on there too. I can add like a link that like here to the workshop schedule. So if Adriano sends me a thing, I can just go to where his is and I'll add a link, you know, and just stick it there so you can click on it and download it.
Thank you.
Well, thank you all for coming to my talk. I hope you had fun. I hope you learned at least something.
Andy says that